Hello, welcome back. So in part three of my talk, I'll prove our main result. So here's the statement again. It's that in the positive curvature setting, the length of the shortest closed geodesic on a two-sphere is bounded above by 3 times the diameter. I've already sort of mentioned the context of the result and said some words about why it's interesting, so we'll get right into the proof. The proof relies on this lemma. So the lemma that we prove is that stationary theta graphs on positively curved two spheres necessarily admit directions of decrease, this is within the space of nets, for the length shortening flow. So in other words, these stationary theta graphs always have positive index, or are unstable critical points of the length shortening flow. And sort of at this point, I imagine you could probably put together a sketch of our proof using this lemma, but I'll do it for you. So we'll run Rotman's proof from the previous video until case 3. And case 3 is where the contraction of the theta graph gets stuck on a stationary theta graph. In her proof, she then appealed to the weighted length shortening in order to sort of argue that such a situation could not occur. For our proof, we'll apply our lemma. So if our contraction ends up getting stuck on a stationary theta graph, we've just shown that such an object has positive index. And so we'll be able to choose the direction in which to continue the length decreasing flow. And so by applying the lemma and avoiding the weighted length shortening, we also avoid the associated increase in the bound to 4 times the diameter. So then sort of Regina's ideas go through, and at every stage the obstruction is a short closed geodesic with length bounded above by 3 times the diameter. That's the main idea. In order to finish the proof, we have to deal with a couple situations. First, you have to make sure that you can't get stuck in an infinite loop where you get to a stationary theta graph, you choose the direction to flow past it, but then eventually you flow back to the same stationary theta graph. This can't happen because the length shortening flow is a strictly decreasing flow, and so you can never return to a theta graph from which you've left. Another situation is accumulation points. So it's possible that we are running our contraction, we get to a stationary theta graph, we flow past it, but then we continue to hit stationary theta graphs. Maybe we hit a sequence of them, which accumulate to some limit object. In that situation, we can apply transfinite induction or Arzelà-Ascoli to show that the limit object is again a stationary theta graph. And so we apply our lemma, we flow past this limit object, and we can continue the contraction down to a point. And then the third idea to deal with, sort of to conclude the proof, is the non-continuity in the restarted flow. So we're contracting our theta graph down, and we're now dealing with a situation where we get stuck on a stationary object and then flow past it. And what that means is that the contraction won't necessarily be continuous with respect to the initial theta graph. It's possible that there are sort of wildly different contractions based on which direction you choose to continue the flow from the stationary object. This was sort of what hung us up when we were sweeping out two cells via the Birkhoff curve shortening process, but we actually don't mind the lack of continuity with respect to the initial theta graph in the contraction of the theta graphs. All we really need is the fact that the set of theta graphs with some bounded length, say 3 times the diameter, is connected, because it's only after we contract the theta graph down to a point that we need to concern ourselves with continuity of the two cell sweep outs in order to guarantee a continuous contraction of the entire 2 sphere. So, right, those are just like some of the points that came up in writing down the details of the proof. So I wanted to share those with you. But at this point, really all that remains is proving this lemma for you. So let's get into that. I'll say that the intuition all comes from the round sphere. So the round sphere has a positive curvature metric. Here's a stationary theta graph on it. I should be able to, according to the lemma, find the direction of decrease. And it's not hard. Let me label these edges 1, 2, and 3. The idea is that I want to pinch edge 1 and 2 together. So here are some sort of vectors in which direction I'm going to pull edge 1 and 2 close to each other while sort of leaving edge 3 unchanged. And if I do this and I vary through geodesics, then the poles will remain fixed and we'll get length non-increasing perturbation or variation of this theta graph. It'll actually have constant length because we'll vary through these great circles and the length of the 3 edges remains constant. So in some sense, this theta graph is degenerate. It admits a direction of constant length. So this isn't sufficient. What I'm also going to have to do is I'm going to pull these vertices together as well. So I'm going to pull this vertex in this direction and this vertex in this direction. And in doing so, I'll find a direction of decrease for this theta graph. Okay, so, I think it's sort of intuitive on the round sphere that if you pull these 2 edges together and you pull these 2 vertices together, that this theta graph will collapse down, to a point, or maybe first to a great circle, and then you can collapse down to a point. The details come when we move away from the round sphere. So let me show you how that works. So in order to prove the lemma, all we really need to do is demonstrate a variation with negative second variation of length. So I want to write down some variational field and some variation such that when I compute its second variation of length, it's negative definite. So I'll start by parameterizing each of my 3 edges. So gamma I for I equals 1, 2, 3, unit speed parameterizations. And here it is. This is the variational field. So I specify a vector field along the first edge, the second edge, and the third edge. And the claim is that if I compute the second variation here, I'm going to get something less than 0. Okay, this obviously came from somewhere, so let me try to explain some of the components of these vector fields. The first thing you'll notice is that I break each vector field up into a component in the direction of motion and a component perpendicular to the direction of motion of the geodesic. And that in these orthogonal directions, they're actually constant vector fields. So a constant vector field +1, -1, and 0. And that corresponds to the intuition that we're trying to pull edge 1 and 2 close together while leaving edge 3 fixed. So +1 is going to pull edge 1 to the right, -1 is going to pull edge 2 to the left, and the 0 in the orthogonal 3 direction will leave the third edge unchanged. And then all I really need to do is cook up the components in the directional motion of the geodesics so that these vector fields will agree at the vertices. So I introduce some cosine functions with the appropriate weights so that when I evaluate these 3 vector fields at the vertices, they agree, and they're such that we're going to pull the 2 vertices towards each other, sort of in the direction of the face that the first and the second edge are sweeping out. Okay, so that's sort of the idea of why these are the vector fields that are working. Next step is to sort of show a few more of the details and then to compute the variations of length. So we have to write down our variations. And the variations, the vector fields agree at the vertices, but I also need variations that are going to agree at the vertices. So why not just exponentiate along in the geodesic direction? So because we're exponentiating along geodesics and the vector fields agree, the variations will agree. And this ensures that the variations are through theta graphs. We wouldn't want to start perturbing our theta graph and have the combinatorics of the object change. So we ensure that the variations agree at the vertices. And then here's some notation. We'll let L of S denote the sum of the lengths of the curves in the variation. And as a first sort of like sanity check, let's compute the first variation of length. So assuming we're at a stationary theta graph, the derivative of this L function with respect to S, evaluated at S equals 0, will be the sum over the three edges of this inner product term with this integral term. And because each of the edges are geodesics, this is an acceleration term, this goes to 0. And this inner product term, this will sum to 0 over the three geodesics precisely because we're at a stationary point where the initial velocity vectors, these vi primes, or sorry, gamma I primes, are balanced. So for the theta graph, they meet at 120-degree angles. And so that'll ensure that when we sum over the three edges, the sum of this inner product is actually equal to 0. So indeed, good. The first variation of length is equal to 0, as we would expect at a stationary object. So just a sanity check. Now let's look at the second variation of length. This is what we're trying to show is necessarily negative. So here I just write it down for you again. We're going to sum over the three edges. We again have this inner product term and this integral term. Okay. Remember we set up the perpendicular component of our variational fields to be not only parallel, but constant. What that means is that this term, this is the covariant derivative of a parallel vector field in the direction of motion, this will be 0. And then we use our positive curvature assumption. Here's our curvature term showing up in our second variation. This term will necessarily be positive, and we're subtracting it. So this entire integral term will be negative. We've just shown that this entire integral term is negative, and so we conclude that the second variation is strictly less than the sum of these three inner product terms. So this term here is negative, and so this second variation is less than the sum of this inner product term. Okay, let's deal with the inner product. So given our choice of variational fields, we actually have that this second derivative is 0. This second derivative actually just turns out to be the derivative in the direction of motion of the velocity vector of the exponentiated geodesic. So this fact is just that geodesics have 0 acceleration. Therefore, this was our inequality from the previous slide. And because this term goes to 0, we conclude that the second variation is always 0. Okay, so again, the idea is at a stationary theta graph, I can always find a direction of decrease. And what I've shown is I wrote down the variational field for you, and by computing the first variation and the second variation, I've hopefully convinced you that in this direction, the theta graph will decrease in length. Okay, so let me just recap the proof real quick. Here's the statement of the theorem. Again, we run Raman's machinery until the contraction of the theta graph gets stuck on a critical point of length, a stationary theta graph. And instead of using the weighted flow, which increases the upper bound on length of shortest closed geodesic to 4 times the diameter, we apply our lemma to continue the contraction. And so this is how we recover the improved bound in the positive curvature setting. I'll say that we can improve our theorem in a couple directions. First, we can move from positive curvature to non-negative curvature. This is just because if you give me a non-negatively curved two-sphere, I can find a sequence of conformally close metrics with positive curvature. Our theorem applies to the metrics in the sequence so that the length is bounded by 3 times the diameter, and then this inequality holds in the limit. So we can improve slightly from positive to non-negative, and then we can also add a nice adjective to shortest closed geodesic. We can show that it's necessarily simple. And this just comes from a result due to Calabi and Cow. They show that for non-negatively curved two spheres, the shortest closed geodesic is necessarily simple. So we get to add this adjective to our theorem. And what's nice about this is that if you remember in the Rotman proof, it was possible that the stationary object that the proof got stuck on, so the obstruction to this contraction, was a stationary figure-8 curve. So that there, the length of the shortest closed geodesic was bounded above by 4 times the diameter, but it was possible that the shortest closed geodesic, or the closed geodesic you were producing, had a self-intersection. So in our proof, now that we introduced this curvature bound, even if that's where the argument gets stuck and the obstruction is a self-intersecting closed geodesic with length bounded above by 3 times the diameter, by this Calabi-Cow result, we're guaranteed of a shorter closed geodesic, which is simple. So it's a nice improvement in the bounded curvature setting. Okay, I'm just going to say a few words about the other main result I shared with you. So this is our pinched curvature result. Here's just the statement again. And really, this result comes from a new isoparametric inequality that we prove. So in the pinched curvature setting, we are able to get this relationship between the area of a two-sphere and the square of the diameter, which depends on the pinching constant. And I'll say that this isoparametric inequality is really just a pinched curvature version of this Calabi-Cow result from 1992. This is also the paper where they show that the shortest closed geodesic on a non-negatively curved two-sphere is simple. So they show their isoparametric inequality is that on a non-negatively curved two-sphere, the area is bounded above by 8 over pi times the diameter squared. So, okay, a couple things to note. First of all, our bound realizes their bound when we set the pinching constant equal to 0. So if the pinching constant is 0, that means you have non-negative curvature, and we recover their result. So ours is a sort of true generalization. I'm not going to take the time to prove the new isoparametric inequality for you, but I'll say it follows very closely the proof of the Calabi-Cow result. So I'll mention that for their inequality, they combine an upper bound on the first eigenvalue in terms of area due to Hirsch with a lower bound on the first eigenvalue in terms of diameter squared due to Zhang and Yang. And so by combining these two bounds on the first eigenvalue, they're able to get this relationship between area and diameter squared. So we follow their techniques and are able to get a pinched curvature version of their isoparametric inequality. Okay, we combine our new isoparametric inequality with the following theorem. So this is a relatively new theorem, and it says for pinched metrics on the two-sphere with pinching constant greater than 0.83, so this is exactly where our 0.83 restriction comes from, then the length of the shortest closed geodesic squared is bounded above by pi times the area. So this is a really nice result. this is a bound on the length of the shortest closed geodesic. And I'll say that it's sort of completely orthogonal to all the bounds we've talked about so far in this talk. So this theorem relies on techniques both from symplectic geometry and Riemannian geometry. It's sort of, completely orthogonal to the ideas we've been talking about today. But we can use the result. So we combine it with the isoparametric inequality from the previous slide in the pinched curvature setting. And just like lining these inequalities up, we get that the length of the shortest closed geodesic squared, bounded above by pi times the area, which is then bounded above by this constant times the diameter squared. And taking the square root of both sides, this is how we formulated the second of our main results. Okay, so that is the end of my presentation. I welcome you to post to the Google group or to send me an email. I'm really interested in your questions or comments or feedback. I hope to hear from you.